Welcome to this explainer. Today we're taking a highly academic, engineering-focused look at one of the absolute most critical challenges of our time, and that's water pollution. We hear about pollution all the time, right? But as engineers, as scientists, as informed citizens, we really need to go beyond the basics. We've got to look directly at the pollution itself. What exactly is in the water? What are we literally pouring into our rivers, our lakes, and our oceans that causes such severe, cascading damage to entire ecosystems? Okay, let's dive into this. As Dr. Arun, a professor of sustainable engineering, brilliantly puts it, understanding the specific types of pollutants is like understanding the enemy in a battle. And he hits the nail on the head there. You need to know exactly what you're dealing with in order to design the right engineering solutions and treatment facilities. So think of this explainer as our tactical breakdown of the exact pollutants that we absolutely must conquer. To do that, we're going to systematically categorize these threats. We'll start with sewage and domestic waste, then move to toxic industrial pollutants, invisible agricultural runoff, physical threats, and finally, petroleum and plastics. And then we'll wrap up by defining the engineer's role in all of this.
All right, Section 1. Sewage and domestic pollutants, the silent killers.
Think for a second about everything that goes down your drain. You've got water from washing, food scraps, detergents, human waste, the whole shebang. Well, this everyday household runoff is actually the single largest source of water pollution in the entire world. And man, it carries a massive biological threat. Sewage is just absolutely loaded with pathogenic microorganisms. We're talking about a highly dangerous cocktail of bacteria, viruses, protozoa, and parasitic worms. When these disease-causing agents manage to enter our water supply, the global health consequences are, well, they're devastating. They act as the direct vectors for typhoid, cholera, gastroenteritis, dysentery, polio, and viral hepatitis. And if you're sitting there thinking this is just a problem confined to developing nations, take a look at this number, 400,000. That is the exact number of people sickened in the 1993 Milwaukee cryptosporidium outbreak. Basically, a sewage treatment plant's discharge contaminated the city's water intake, and the plant completely failed to filter out the parasite. At least 104 people died. It is a really terrifying, stark reminder that even our most advanced modern treatment systems can fail, and when they do, the consequences are catastrophic. Now, what's really interesting about this slide is seeing how sewage isn't just a biological hazard. It's a profound chemical and nutrient threat as well. Walk through this chain reaction with me. Sewage introduces massive levels of plant nutrients, specifically nitrates and phosphates, right into the water. These act exactly like fertilizers, triggering an explosive growth of algae. Then, when all that algae inevitably dies, bacteria come in to decompose it. This decomposition process literally sucks the dissolved oxygen right out of the water. Ultimately, fish and other aquatic life just suffocate. This process, known as eutrophication, quite literally turns a healthy, thriving water body into a green, lifeless soup.
Moving right along to Category 2, toxic industrial pollutants, the toxic cocktail.
For decades, unfortunately, waterways were treated as free dumping grounds for untreated industrial effluents. And this resulted in a terrifying mixture of substances. Looking at the breakdown here, on one side we have heavy metals, elements like chromium, arsenic, lead, and mercury. Now these aren't organic materials that will naturally break down over time. No, they persist in the environment forever. They accumulate in the food chain and cause really severe health problems like birth defects, genetic mutations, and cancers. Contrast that with the hazardous organic and inorganic wastes, things like acids, alkalis, cyanides, and chlorides. These are acutely, directly toxic to both aquatic life and humans almost immediately upon exposure. The ultimate consequence of this kind of industrial negligence is captured perfectly in the Minamata Bay tragedy, which happened in Japan between 1953 and 1960. A chemical factory systematically released mercury into the bay, and the local people, who heavily depended on the bay's fish for their daily food, began suffering from horrific neurological disorders, severe birth defects, and even death. It became the global symbol of industrial pollution. And this brilliantly illustrates mechanically exactly how the Minamata tragedy unfolded. The factory released the mercury, sure, but then bacteria in the water converted it into an even more toxic form called methylmercury. Look at how it moves right up the chain. Algae absorbed it, fish ate the algae, and finally, humans consumed the heavily contaminated fish. This wasn't just a chemical problem, folks, it was a profound failure of engineering design. The factory simply lacked a system to capture its own waste, and the surrounding environment paid the ultimate price. Okay, let's shift to Category 3. Invisible agricultural pollutants, the invisible runoff. Now, while a factory is a specific point you can isolate and point a finger at, Agricultural waste is notoriously difficult to control. Why? Because it's a diffuse, non-point source of pollution. When heavy rain falls on massive farmlands, it picks up a really dangerous load. First, you've got manure and fertilizers, which, as we learned earlier, lead directly to eutrophication. But actually, it gets worse. Consuming water with high nitrate levels is incredibly dangerous for infants. It causes a terrifying condition known as blue baby syndrome, where the infant's blood literally loses its capacity to carry oxygen. Then, the runoff picks up pesticides, chemicals like DDT, dieldrin, aldrin, and malathion. These are specifically engineered to kill insects and rodents, but when they wash into our streams, they act as broad-spectrum toxins to almost all aquatic life. The real underlying danger with these pesticides is biomagnification. You see, many pesticide residues aren't actually soluble in water, but they are highly soluble in fats. So when a small fish eats contaminated algae, the pesticide dissolves and stores right in its fatty tissue. Then a larger fish eats that fish, and the concentration spikes. This process magnifies all the way up the food chain until the absolute highest, most lethal concentrations end up right on our dinner plates.
Category 4. Physical pollutants: heat, sediment, and radiation. So far, we've focused heavily on biological and chemical agents, but pollutants don't always have to be chemical to destroy an ecosystem.
Let's move to and see how this builds into a complete ecological disruption. First up is thermal pollution. Power plants frequently discharge hot, cooling water straight into rivers. Well, warmer water naturally holds less oxygen, and that sudden blast of heat can actually kill fish instantly through thermal shock. Second, we have sediments. Mud from deforested lands or croplands washes into the water, blocking the sunlight that aquatic plants desperately need to photosynthesize and physically clogging the gills of fish. Finally, maybe the most frightening, radioactive wastes. Radioisotopes, like radium and potassium-40 from mines and nuclear labs, enter the water. Over time, this radiation accumulates in human blood and vital organs, directly causing tumors and cancer.
Moving to Category 5. Petroleum and plastic pollutants, the modern scourge. These are really the materials synonymous with our modern age, the persistent, defining environmental hazards of the 21st century.
When we look closely at petroleum pollution, it really comes in two distinct forms. On one side, we have the dramatic, acute events, oil spills from ships and pipelines. These cause massive, highly visible damage, right? Oil slicks, coating animals, causing immediate death to marine life. But on the other side, we have chronic pollution. This is the constant, quiet, diffuse release of small amounts of oil from places like refineries, exploration sites, and even everyday auto shops. It's definitely not as telegenic as a major spill, but it acts as this continuous, insidious baseline of contamination in our waterways.
And then, of course, we have the plastic crisis. Plastics are forming literal massive floating patches out in our oceans right now. The physical structure of plastic leads to ingestion and entanglement, causing horrible injuries, blockages, and death for marine life. But the real engineering nightmare here is that plastics don't biodegrade. They don't just disappear. They simply break down into increasingly smaller, pervasive particles that we call microplastics. And these microscopic particles are now found absolutely everywhere, from the deepest ocean trenches to the tap water you drink in your own home. The long-term health effects of this internal plastic pollution are still being actively studied. But let me tell you, the initial findings are a major cause for alarm.
Finally, Section 6. Conclusion: the engineer's role. Taking all of this in, it is so easy to just fall into despair. But this is not a story of environmental defeat. No, it's a story of strict professional responsibility and incredible engineering opportunity. So, the crucial point is this. As civil engineers, as scientists and informed professionals, this is your calling. You are the ones who must design the advanced systems to capture, treat, and scientifically neutralize these pollutants. Your mandate is to engineer solutions that prevent this waste from ever reaching our rivers and oceans in the first place. The Minamata tragedy, the Milwaukee cryptosporidium outbreak, the deoxygenation of our lakes, these aren't just sad historical stories. They are solvable design challenges. We absolutely must take responsibility for the full life cycle of every industrial and domestic process we build.
The world desperately needs people who truly understand these pollutants on a deep level and can design the next generation of systems to manage them. So, I'm going to leave you with this final thought and challenge. Pick one of the pollutants we discussed today, look at the data, understand its mechanics, and ask yourself, how will you engineer the solution? Let's build it better. Thank you so much for watching, and I'll see you in the next explainer.